Alright, good evening. Welcome to lecture 1.8 of Unit 2, Nuclear Fusion. Here are the learning intention and success criteria for this chapter. Please pause the video and attempt to complete the KS table down the side there. Alrighty, so having looked through here, we can see we've got to be talking about nuclear fusion. We need to be talking about energy outputs and comparing, and we can see our calculate verb pop up there as well. So we need to know, well, what is nuclear fusion? We should be able to go, well, how do these two things compare with each other, because we need to talk about their energy outputs. And finally, under skills, well, can you calculate the energy in a fusion reaction? So firstly, in video 1.6 of the unit, I discussed how the stability of an atom can be looked at on a basis of its binding energy per nucleon. I've abbreviated there to Be per N. Now, radioactive decay occurs because of this property. Nuclear fission occurs when a highly unstable atom can become two smaller, more stable atoms because of their binding energy per nucleon. And finally, fusion is energetically favourable because the binding energy per nucleon increases as you move from a higher mass to a lower mass totality. So as such, if you're unsure about how to calculate binding energy, you will need to go back and have a look at that other video, because that's kind of key for looking at both fission and fusion. So nuclear fusion is defined as when two or more atoms combine to make one or more heavier atoms and some subatomic particles. In essentially most forms that you're going to be seeing is that you get two atoms, you shove them together, you make one bigger atom, and maybe you get a proton or a neutron or electron getting spat out of it. Now, when we looked at bombardment in the couple of previous videos, that was fusion. We got two atoms, we shot one into the other, and they became one. That's what fusion means. Now, after that, often either it might fission, like we saw with uranium-235 when it gets hit with a neutron in the previous video. Sometimes you might just have radioactive decay, like carbon-14. So carbon-14 is made when there's a nuclear fusion event in the upper atmosphere, with nitrogen being collided with a single neutron to become carbon-14. Plus a hydrogen atom that gets spat out of it, but there's this fusion event to become firstly nitrogen-15, and then decays into carbon-14. And then sometimes you get something stable, like when helium-3 is formed in the sun. Now our sun does run on nuclear fusion. Hydrogen nuclei, deuterons most of the time, H2, they merge to create either helium-3 or helium-4. So things like this, where we might have a deuteron plus a hydrogen becoming a helium-3, or two deuterons smashing together to become a helium-4. And we can do the same type of calculations using isotope masses that we did with nuclear fission to determine what the mass deficit is, and then determine how much energy is released. So let's have a look at this example here. So this one is from page 197 on your text. So consider the following fusion reaction. We have here even bigger, that's a little bit fuzzy, so I'll just read off the text. We have a H2 plus a He3 becoming a He4 plus one hydrogen plus some gamma ray. And the first type of question is a little bit different from ones that we've really seen before, and it asks, show that the energy released is 18.35 mega electron volts. Now this is when you see something like this where show the energy is released, it's saying calculate the energy. But what it's saying is that, well, this is what the answer will be, so you'll know whether or not you're right. The reason for this is because part B and C needs you to use that energy. Now you might look and go, I don't know how to do that, but I can do parts B and C. So that way, if you can't do part A, you're not stuffed for parts B and C. This is sort of a very common tactic for multi-part questions that you'll probably see on your final exam. Well, it definitely will next year in Year 12, or your Year 12 final exam, depends on when you listen to this, I guess. But for Year 11, it's certainly a technique that I would use if I need you to use something that you work out at the start of a question for something down the track. Okay, and it's kind of a clue as well. If you see a question that reads, show that the energy released is this, or show that some number is true, you can be basically certain that I need to use that number at a secondary or third part of this question. So, we need to show the energies released. We have a H2 and a He3, so we're going to need the isotope masses for those first. So, H2 is equal to, and from the back of the text, is 2.014102, and He3, sorry, that should be U for atomic mass units, is equal to 3.016029. Now, you have to use as many digits as you are given for these things, because generally the difference is going to be somewhere down this sort of region. And if we add that all together, the mass of our products is equal to, mass of our products. Oh, they're using, mass of our reactants. Never mind, I'm having a stupid moment. I always get those two mixed up. Mass of the reactants is going to be equal to 5.03031 U. Now, on the other side, we have a helium-4 and a hydrogen-1, and we're trying to prove what the gamma is. So, He4, H1, He4 is equal to 4.002603, and H1 is equal to 1, because it's just a single proton, 1.007825. That is something that may occur to you. They won't say specifically the mass of hydrogen 1 is equal to this, because if you're reading this going, oh, H1, hydrogen's the first thing, it's only got one proton, so it's got one nucleon, and the mass of one proton is equal to this. So that is something to sort of keep in mind whenever you are doing some of these things. And finally, the mass of the products, you add these together, will be 5.01. So you can see here the difference is at the second decimal point. 5.01042804280428. And if we take the mass difference of these, so this is our final, this is our initial, the difference will be something like negative 0.019703. You might go, well, how could we lose mass? Remember that mass is being converted into energy. Okay. Now, if you look at the text on this, it actually is giving you the definition for how much energy is equal to one atomic mass unit. So one atomic mass unit is 931.5 mega electron volts. So, they've done a conversion here to basically go, well, if I take this number, I multiply by the amount of mass, because I have this many atomic mass units, and one atomic mass unit is 931.5, well, I get my final answer, and they show that it's correct. However, you could turn this into kilograms first, so we'd have to know, well, what is the mass of, mass in kilograms of one atomic mass unit, convert that into kilograms, and then from there we could turn it into joules using E equals mc squared, and then turn that energy into electron volts. So you could get there, it would just be a very long step around. So, while I would encourage you to sort of just memorize the 931.5 electron volts, just in case you need it, I will show you how to do it using the longer version, because the as far as I know, and I'm about to just load up the formula booklet, as far as I know, the conversion for mass to mega electron volts is not actually given to you. The joules to electron volts is, but no, under the rest of it, you just got mass of those. Okay, so let's do it the long way. 1U equals 1.66 times 10 to the negative 27 kilograms. So if I take the 0.019703, I don't care the fact it's negative. Negative just tells me that, yeah, this gives off energy. Times 1.66 times 10 to the negative 27 equals gives me 3.270698 times 10 to the negative 29 kilograms. Using E equals mc squared equals mc squared. So here's our m value. E equals times 9 times 10 to the 16 gives me 2.943 times 10 to the negative 12 joules. Now remember, 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. So 1 EV equals 1.6 times 10 to the negative 19 joules. Remember that is inside your data booklet, so it's something you can look up. I need to turn this into electron volts, so since 1 electron volt is equal to this many joules, I need to know how many times does this go into that. So I'm going to divide my answer in E in my joules value by my electron volt constant divided by 1.6 10 to the negative 19. We get, well, this is good, we're on the right track, 18. We've got 1, 2, 3, 4. Okay, so it's 18 times 10 to the 6, or 18 point. Let's go round it off to 4. Because what are we trying to prove it equals to? We're trying to prove it equals 18.35. Ooh, 18.397 times 10 to the 6 electron volts. Now 10 to the power of 6 is mega. 18.397 mega electron volts. Now, okay, well, why is our number a little bit different? The reason our number is a little bit different is because I've carried through these numbers the whole way. I haven't done any rounding off at all. Secondly, the 931.5 mega electron volts is a approximation. Like there would be more decimals on it, but Richards here has just used that value as a kind of a quick reference there. So this one to me, if I was to ask you, prove that it equals this, and that was the answer that you got, or that was the answer I got, I'd be going, yep, that's close enough. Therefore, it's correct, or therefore I've shown that this, because 18.39 is, or 18.4 is approximately 18.35. Okay, it's within rounding error, is the way I would phrase it, and so therefore, you've demonstrated the correct value. Okay. Let's go on to part B. Unfortunately, I have to erase this manually. Actually, all I'm going to do is do it the fast way. Discard. And let's recreate it. There we go. Second part is asking me to show that the energy as joules per atom. So they've actually gone and, next step here, they've gone and worked out the joules in terms of, we've worked out part B as part of our doing part A the long way. So that's good for us. We've already worked out part B. I'm just going to write the answer for part B up here. B is 2.944 times 10 to the negative 12 joules. So if you have a look at the worked example in the text, it goes, energy joules equals mc squared. They've used m equals the atomic mass value that we worked out before, multiplied it by the 1.66 times 10 to the negative 27, which is the conversion between atomic mass and kilograms, and then multiply that by c squared in order to get their answer. Okay, and so that gives us that number there. The last bit is energy per kilogram. Okay. This is, again, one of these really annoying sort of workings out here. So they've got mass of atom, and the thing is, if you do a bit of chemistry, you can probably do this at a little bit more elegance, but we're going to do it from first principles. So we know the mass of, so for energy per kilogram, why is it worked out in terms of H1? H1 is not inside. Oh, express this as no H2. It made a typo. Okay, so the working out has mass of one atom of H1 is equal to 2.01, blah blah blah. However, if we look up at where we looked at the isotope mass for the reactants, that's actually the mass of H2. Okay, so mass of H2 equals 2.01, 4102 atomic mass units. We're going to multiply that by our conversion factor, 10 to the negative 27, gives us a mass of 3.3434 times 10 to the negative 27 kilograms. And yes, all those numbers match up. Okay, so that is the mass of one atom. We need to know how many atoms are actually going to be in a kilogram of stuff, so then we can work out how much energy is released per kilogram. So if I take my 1 kg and I divide it by my 3.3434 times 10 to the negative 27, that will give me, because they're both kilograms, so the units will cancel, that has to give me a counting number, and in this case will give me 2.9909 times 10 to the 26 atoms. Okay, this is a fairly common technique, the idea that you need to work out how much count of something there is, and you need to divide a couple of units in order to do that. So we've got the number of atoms. Now we have the energy. To work out energy per kilogram, well, we know how many atoms there are, we know how much energy is being worked out per atom, and so if we multiply these two numbers together, we'll be able to work out the total number of energy per kilogram of atoms. So I'm going to take this number, and I'm going to multiply it by this number up here. So 2.9909 times 10 to the 26, multiply it by 2.944 times 10 to the negative 12 joules, gives me an answer of 8.804 times 10 to the 14 joules of energy. So, you know, that's a fairly large amount of energy for a kilogram of hydrogen. A kilogram of hydrogen is a fairly small amount of gas. And hydrogen cars will probably be something of the future. Okay, now, one example of the syllabus is that you need to be able to compare fusion and fission reactions, okay, in terms of their energy. Now in 1.7 I did an example of a fission energy calculation, and you can go back to chapter 6.2 of your textbook if you need to look it up in that. And now we've just gone through a fusion video calculation to have a look at. Now page 197 has some working out at the bottom there to basically getting the energy released from the fusion of 4 hydrogen 1 atoms into a hydrogen 4 atom plus some beta positive particles. Have a look at that, but I want to look at this table as the focus here. So this table is at the top of page 198 if you need to be clear. It looks okay to me. Now, it looks at the fission of uranium-235, here's our first column here, and it looks at the fusion of 4 lots of hydrogen-1. And it looks at it in terms of per event, okay, how much energy in joules is released per one event of either fission or fusion. It looks at it in terms of per kilogram. Now, as you can see though, one atom undergoing fission releases a lot more energy than a single fusion reaction. Okay, so we can see it over here. Fission is 7 times the amount of fusion. But if you take 1 kilogram of each and you do the same thing, you can see that 1 kilogram of hydrogen atoms here releases a lot more energy than 1 kilogram of fusion. And if we consider the masses, we can see why. Uranium-235 has 50 times the mass of 4 hydrogen atoms. So you get a lot more fusion events for the same mass of 1 fission event. And you need to know that result. So per kilogram, fusion reactions produce more energy than fission because a larger percentage of mass is converted to energy. Okay, being able to prove it might be useful, but you do need to know it. Finally, you've got to recall this graph about binding energy per nucleon. As you can see, as you move from hydrogen up to iron, the binding energy per nucleon increases. So that means the stability increases. It also means fusion is energetically favourable, and this is why stars stop at iron, because fusion doesn't produce energy anymore, so it starts to cool down as it makes the elements a little bit above it. Alright, so in this lesson we have gone through the following. We have defined our nuclear fusion, we have calculated the mass defect of a fusion reaction to determine the energy that's released, and finally we've compared the energy production of fission and fusion reactions on a per event and a per kilogram basis. For your entrance to class, please complete questions 1 to 3 in chapter 6.3 Check Your Learning PDF, and copy those answers into the 2.1.8 space on eLearn. Thanks very much for your time, have a great evening.